I'm Herb Gross, and welcome to Lecture 14 in our Gateways to Algebra series, where today we're going to look at two enrichment examples. Basically, what I'm going to do is to pick two examples, both of which I think are interesting, and show how formulas are developed. Now, what happens to most students is they say, wow, that's interesting, but I don't think I ever could have done that. Well, that may or may not be true. You'll never know until you become more experienced. But the important thing is that in most fields where people have to use algebra, and they have to use it in innovative ways, there's usually a formula given. And if you trust that formula, it's just a matter of carrying out the recipe. You know that start with X, do this, do that, and the answer is what you're looking for. So let me pick a couple of examples, one of which is an interesting piece of folklore, which we don't have documented, but it's told as a true story concerning the mathematician Gauss. And it's told that when Gauss was in school, being very bored with school, he very soon became a discipline problem and would talk and whisper and stuff like this. And the teacher, to sort of teach him a lesson, punished him by giving him an arithmetic problem to do that she thought would keep him occupied for a long time. And this may be a paraphrase. I don't know exactly the situation, but it goes something like this. The teacher, as a form of punishment, said to Euler, to Gauss, why don't you add the first 100 numbers? In other words, 1 plus 2 plus 3, all the way up to 100. Now, that's a very, very ominous task for a person to tackle. Not only that, there doesn't seem to be a real clever way of doing this problem. In other words, if you do this problem by brute force, what do? You say, okay, we start with 1. 1 plus 2 is 3. Then we add on 3, and that gives us 6. Then we add on 4, and 6 plus 4 is 10. And we just keep on going all the way till we've added up all 100 numbers. And can you picture how tedious that's going to be? Okay? And she figured that would keep Gauss quiet for a long time. And as the story has it, Gauss simply looked at this problem and watch what he did. He said, look, all these numbers keep increasing by 1. So look what happens. The second number is 1 more than the first number. Okay? And the last number is 1 more than the next to the last number. So he says, look at, if I add these numbers up in pairs, look at, the first plus the last is going to add up to 101. Now what about the second and the second from the last? This is 1 more than this. The 99 is 1 less than the 100. That's also going to add up to 101. See, 2 plus 99 is 101. How about the third and the third from the last? 3 plus 98 is 101. And so here was the clever thing that Gauss discovered. He said, look, if I start at the ends and work in, each pair of numbers adds up to 101. Okay? Now there's 100 numbers altogether, and it takes 2 to make a pair. 100 divided by 2 is 50. Therefore, if each of the pairs add up to 101, and there are 50 of these pairs altogether, all I have to do is multiply 101 by 50 and gave, what, 5,050 as the correct answer. Now this is a rather amazing result. Notice what happens over here. To do this problem, you didn't have to add all these numbers up separately. There was a formula. It basically said what? Take the first one, add it to the last one, and then multiply that by the number of pairs, which is half the number of terms. So more generally, it would look something like this. Suppose instead of adding up to 100, we just let n stand for the last number. So it's 1 plus 2 plus 3 plus 4, all the way up to whatever number you want to stop at. We're going to call that n. And what Gauss next said was, look, it doesn't matter whether you stop at 100 over here. The first number plus the last one is going to be the sum of all those. Each of those pairs is going to have to do the same thing. Now the difference is when this was 100 and you wanted to add 1 onto it, you just called it 101. If this has been 60, you add 1 onto it, it would be 61. When it's represented generally by n, all you can say is what? N plus 1 is n plus 1. See, so that's the sum of each pair. Now if there are n terms altogether and it takes 2 to make a pair, n divided by 2 is the number of pairs. And so we simply took what? The sum of the two extremes, the 1 plus the n, and multiplied that by the number of pairs, which was n over 2, and therefore we get a formula that looks like this. By the way, Gauss didn't stop there. See, what's interesting about people with mathematical minds is once they see something, they say, could this problem have been generalized? See, why was he able to add the first and the last and say that would be the same sum as all the other pairs you would get? And the answer is nothing to do with this starting with 1. It could have been any number you started with. It also had nothing to do with the increase being 1 each time. The important thing would be that you could start with any number you wanted, but the increase had to be the same each time. Like, for example, suppose the second number was 7. Well, the difference between 3 and 7 is 4, so the next number would have to be what? 7 plus 4 is 11, 11 plus 4 is 15, 15 plus 4 is 19, 19 plus 4 is 23. This is called an arithmetic sum, meaning that you can start any place you want, but the difference between two consecutive terms is always the same, in this case 4. So let's see what happens over here. Suppose I write down the first 6 numbers in this progression. It's 3, 7, 11, 15, 19, and 23. Could I add these up the long way if I wanted to? See, 3 plus 7 plus 11 plus 15 plus 19 plus 23. And just checking the arithmetic over here, it's not difficult to see that the sum is 78. Now, here's the way Gauss would have done this problem. He would say, look, the first term is 3, the last term is 23, so that pair is going to add up to 23 plus 3, which is 26. He says each of the other pairs chosen in this way will also add up to 26. Just as a check, let's notice that. The 7 is the second term, 19 is next to the last, 7 plus 19 is 26, that checks. 11 plus 15 is also 26. So what Gauss would have said was, look, instead of adding up these 6 numbers, just do what? Add the first and the last, which is 23, and multiply that by 3, because that's the number of pairs. 26 times 3 is 78. See, let's try it with another one, just to see if you really get the idea. And first of all, let's summarize how we could do this. See, the first term could be whatever you wanted. Let's start with a 4 this time. Let's make the constant difference 5 this time. So it would be what? 4 plus 5 more is 9, plus 5 more is 14, plus 5 more is 19, etc. And let's suppose we add these all the way up to 49. Now, according to Gauss, what you do is what? Add the first term and the last term. The 4 plus 49, that's going to give you 53. How many terms are here altogether? 2, 4, 6, 8, 10. You're using 2 to a pair. 10 divided by 2 is 5. So what do you have? 5 pairs, each adding up to 53. And by the way, do you see the 5 pairs? It's the first and the last, the second and the next to the last, the third and the third from the last, the fourth and the fourth from the last, and then the fifth and the fifth from the last. You see how they're working this way? So in other words, in general, what did you do over here? Whatever the first term was and whatever the last term was, you added them together. See, the first plus the last. And then what did you do? You multiplied by the number of pairs. Well, if there are n terms, there are n over 2 pairs. By the way, if n is odd, you don't get an even number, a whole number of pairs here, but interestingly enough, the formula still works, so let's not worry about that special case. But watch how the formula works now. See, the first is 4, the last is 49. Let's put those in over here. See, this would be 4, this would be 49, and the number of terms would be 10. So 10 over 2 would be 5. 4 plus 49 is 53. 5 times 53, or 53 times 5 is 265. And what that says is, if you added all these numbers up, you would get 265 for the answer. By the way, once you understand how to read this formula, it's an arithmetic problem. See, it says what? Take the first term, add it to the last term, and multiply that by what? The number of pairs, half the number of terms, and that will be the sum, see, S. Now, algebra comes in if you're given the sum, but you're not given all of these numbers. For example, suppose I were to say to you, solve for n if S is 265 when F is 4 and L is 49. Well, see, again, you just replace everything by its given value. You're told in this problem that S is 265, so you replace it by 265. You're told that this is true when F is 4 and when L is 49, so you make those substitutions. And now notice that the only variable you have over here is n. Let's simplify this as much as possible. This is 265. 4 plus 49 is 53, and there's a 2 in the denominator. So this says that the right-hand side is n times 53 over 2. Now remember, we have all kinds of rules of the games to use here. If you don't like fractions, what's nice is multiply by whatever the common denominator is. Since there's a 2 downstairs, why not multiply by 2 upstairs? The 2 here would cancel with the 2 here. But in an equation, if you multiply one side by 2, you also have to multiply the other side by 2. So what would happen here? The 2 times the 265 would give me 530. The 2's here would cancel, and that would leave me with 53n. Now, if 530 equals 53n, to find n by itself, I have to get rid of the 53. Since the 53 is multiplying the n, I'm going to have to divide by it. If I divide by 53 on one side, I also have to divide by 53 on the other side, and I get what? N is equal to 10, which certainly checks with the fact that we had what? 2, 4, 6, 8, 10 terms. Okay? Now, let's just pause here for a minute. That's the first example. Wasn't that kind of a fun type of thing? I mean, can you see young Gauss's mind working on this? Can you see the poetry, the innovativeness, the fact that there was nothing cut and dried about this? What was nice is that once he got this result, could he summarize his results in a formula that was cut and dried, and a formula that anybody could apply once they understood how you read a formula and what you mean by the rules of arithmetic. You see, people who could not develop that formula could certainly use that formula. And what's even more important is, suppose you didn't even know where that formula came from. See, suppose all I said to you was that S is equal to n over 2 times F plus L, and find the value of n when S is 265, F is 4, and L is 49. You don't even have to know where that formula came from to be able to use it. So when people say, I can't do this subject because it uses a math formula, remember, the formula has already been done for you. The hard part would have been to derive the formula. See, a very common place that this happens is in converting Celsius to Fahrenheit on a temperature scale and vice versa. So in the rest of this lecture, let me show you how the Celsius-Fahrenheit relationship formula comes about, and then to point out to you how you can solve for different values of Celsius knowing Fahrenheit and vice versa without even knowing where the formula came from, as long as you accept the formula and remember how we work with them. So let's just take a look at this as Fahrenheit versus Celsius, okay? Fahrenheit and Celsius were the names of two people. Fahrenheit was a Danish physician, lived in Copenhagen. Celsius was the man who invented what we now know as the centigrade scale. When I went to school, we didn't say Celsius, we said centigrade. And centigrade is not a person's name. Centi stands for 100, and grade is degrees. So centigrade was based on 100 degrees. One of the reasons that we changed this name is that the Fahrenheit temperature scale was also based on 100 degrees, but it was done in sort of an obtuse way. Let's first of all discuss how a thermometer works. In general, heat expands objects, liquids, and cold makes them contract. In other words, when you heat a liquid, it expands. When you cool it, it contracts. There are some exceptions to this. But for the most part, this is a general rule. So what happens was, you could measure how much temperature changed just by watching how much a liquid either contracted or expanded. The problem is that when the average liquid expands when you heat it, it's so gradual that you won't even notice it unless there's a huge, huge temperature change. For example, if you're heating a pan of water on a stove or something like this, and the water heats up, prior to it boiling, you don't notice the water level getting any higher. So what they do to make a thermometer is they take a very, very thin tube. In other words, they take something and bore a very thin hole in it, very, very narrow. So what happens is, when you put the liquid in this tube, if that liquid expands or contracts, since there's no place for it to move laterally, it either has to do what? Move up if it's expanding, and to move down if it's contracting, okay? So basically, the way you're going to measure temperature is by watching how this mercury level changes. So let's take a look over here. Here's what Fahrenheit did. Fahrenheit wanted to measure the temperature in his town. What was the temperature like on a typical cold day? He didn't like negative numbers. So what he did was, he put the thermometer outside his window on a very, very cold day in Copenhagen. And what he did was, when he woke up that morning, he noticed to see where the mercury level was. See, it came up to here. So he simply called that 0 degrees on his scale. See, the F stands for, this is how Fahrenheit measured it. So what was 0 degrees according to Fahrenheit? It was a particularly cold morning in Copenhagen. In fact, if he had been lucky enough to find the coldest possible morning in Copenhagen, there never would have been a temperature in Copenhagen of less than 0 degrees. See, the fact that the temperature goes below 0 on the Fahrenheit scale means that the day that Fahrenheit made up a scale wasn't the coldest it ever gets. You see the idea this way? So that basically what did happen was, if he had called 0 degrees the temperature on a hot day, you see on most days the temperature would have been below 0. The fact that Fahrenheit was pretty good is indicated by the fact that most of us don't see that many below 0 days in the course of a year. Now he also needed another point to get a scale. You need 2 points to make a scale. So he had a 0 point, now he needed a 100 point. And what he did for a 100 point was he took his own body temperature. In other words, he took his temperature, and whatever the mercury level came up to at that point, he called 100 degrees Fahrenheit. By the way, as an interesting piece of folklore, if Fahrenheit had measured his temperature accurately, or if he didn't have a fever that day, normal body temperature would have been 100 degrees Fahrenheit. Notice that the normal body temperature that we often talk about is 90.6 degrees on the Fahrenheit scale, and that roughly corroborates the fact that Fahrenheit called his body temperature 100, okay? So now he had this particular scale. Now, who really cares about a cold morning in Copenhagen or what Fahrenheit's body temperature was on a particular day? What was really important to Celsius, he said, look, let's get a 0 and a 100 that we can reproduce in the laboratory whenever we want to. See, we don't know what that day was in Copenhagen. We don't know what body temperature Fahrenheit's going to have on a particular day. And if Fahrenheit ain't here, we don't even know what his body temperature is. Let's pick something that all scientists can measure. So what he did was he went into the laboratory and he measured the freezing point of water. Now, by the way, if you want to know how that's done scientifically, you put a thermometer into a tube of water and you keep adding ice to the water. And as the ice is being added, the temperature comes down because the water is cooling off. Now what happens is, as that water starts to turn to ice, all of the energy that was lowering the thermometer, the temperature, now goes into converting the water from liquid into solid. In other words, it's going to go from water into ice. And what that means is, as you now look at the thermometer, it will appear that nothing is happening. In other words, the temperature level will stay the same until the water has frozen solid. So basically, what Celsius did is he went into the laboratory, measured the freezing point of water. And that's the thing that he called 0, because he said, look, any scientist in the world can reproduce that particular condition. Then he says, now we need a boiling point. Well, you still get the water there, now heat the water. As you heat the water, you see the temperature rise. When it gets to a certain point, it starts to boil. And what boiling means in scientific terms is that the water is being converted from liquid to gas. It's turning from water to steam. And to convert the water into steam, the temperature stops changing, and all that heat energy is used to make the transference in state. So again, as you heat the water, you keep watching the temperature, the mercury level rise in the tube. And as soon as it levels off and stops rising, that's the boiling point. So that's what Celsius did. You see, 0 was the freezing point of water on his scale, and 100 was the boiling point. Now, it turned out that the freezing point of water, let's see if I have it on the scale here. It turns out that the freezing point of water was considerably warmer than the coldest day in Copenhagen. In other words, on the day that Fahrenheit hung his thermometer out the window, the chances are, if there was liquid on the ground, it had turned into ice. It was colder than the freezing point of water. In fact, if you now took Fahrenheit's thermometer and immersed that into the freezing liquid, what read 0 on Celsius scale would read 32 on Fahrenheit scale. So now suppose what happens is you're taking a temperature reading. The way you're going to measure the temperature is by how high the mercury level rises. Now here's the thing. On the Celsius scale,
Let's just measure above the 0 on the Celsius scale. On the Celsius scale, you're measuring from 0 to whatever the Celsius reading was. Notice that on the Fahrenheit scale, if you call that reading F, this is not 0, it's 32. So to find the height of this column in Fahrenheit degrees, it's not enough to say F. It's what? It's only, see, you want to measure the same height. So it's from here to here, so it's F minus 32. That's where the F minus 32 comes from. Secondly, notice that it takes 100 degrees Celsius to do the same job that 200, by the way, I didn't mention that, I should have. It also turns out that not only is the freezing point of water 32 on the Fahrenheit scale, but the boiling point, which is way higher than Fahrenheit's body temperature, came out, in fact, to over double that, to 212 degrees Fahrenheit. See, Fahrenheit never said, let the boiling point of water be 212. He never said, let the freezing point of water be 32. He picked his own 0 to 100, and on his scale, the freezing point of water was 32, and the boiling point was 212. Now watch what this means. See, to go from the freezing point to the boiling point of water on the Celsius scale, that was 100 degrees, wasn't it? But what was it on the Fahrenheit scale? On the Fahrenheit scale, you're going from 32 to 212. 32 from 212 leaves 180. So in other words, you have to go what? 180 degrees on the Fahrenheit scale to do the same thing that would be 100 degrees on the Celsius scale. So what's that ratio? 100 over 180 reduces to 10 over 18, and that in turn reduces to 5 over 9. And so what this says is, if you start with the Fahrenheit temperature, first of all subtract 32 to adjust the 0 point, and then since it takes what? 9 Fahrenheit degrees to make up 5 Celsius degrees, simply multiply that by 5/9. In other words, what this showed is that the relationship between Celsius and Fahrenheit is that starting with the Fahrenheit, you subtract 32, multiply by 5/9, and that gives you the Celsius temperature. Now, it's interesting to see that derivation. It's interesting. But suppose you didn't know that, but you were willing to accept that your science teacher wouldn't lie to you. And so you're told, if the formula relating Celsius to Fahrenheit is given by such and such, find the Fahrenheit temperature when the Celsius temperature is such and such. You follow the idea? In other words, the problem might look something like this. Given that C is 5/9 of parentheses F minus 32, find the value of C when F is 77. And by the way, let me pause here for a moment and have you notice that the word Fahrenheit and Celsius doesn't appear here. Even if you didn't know what F and C were in this problem, should you still be able to evaluate C when F is 77? All this says is what? Start with F, subtract 32, and multiply by 5/9. And if fractions bother you, multiplying by 5/9 is nothing more than multiplying by 9 and dividing by 5. So starting with 77, you first subtract the 32, so subtract the 32, then divide that answer by 9, and then multiply that answer by 5, and that will give you the answer. 77, subtract 32 is 45. 45 divided by 9 is 5. 5 times 5 is 25. Therefore, when F is 77, C is F equals 77, makes C equal to 25. And if you happen to know that this is the formula relating Fahrenheit to Celsius, then you know what? When it's 77 degrees on the Fahrenheit scale, it's 25 on the Celsius. And by the way, the only difference between arithmetic and algebra is that it becomes algebra when you're given the output and have to reconstruct the input. In other words, the formula stays the same. In other words, what does it say? It still says what? Starting with F, subtract 32, multiply by 5/9, and the answer is C. But suppose they say find the Fahrenheit reading when the Celsius reading is 20. See, now they're giving you that the Celsius reading is the 20. The C gets replaced by the 20. Now the F is scrambled in with the remaining numbers. So how do you solve for F over here? You say, well, the F is protected by the parentheses. I first have to unblock the parentheses. Since the parentheses is being multiplied by 5/9, I have to divide by 5/9. And dividing by 5/9 is the same as multiplying by 9/5. But if I multiply by 9/5 on one side, I have to divide by 9/5 on the other side. 5 goes into 20 4 times. 4 times 9 is 36. Now I want F by itself. What have I done here? I've subtracted 32. To undo subtracting 32, I have to add 32. If I add 32 to this side, I get f. If I had 32 to this side, f must be 68. As a check, 68 minus 32 is 36. 36 divided by 9 is 4. 4 times 5 is 20. And so therefore, I have now used this formula algebraically because I was given the output and had to find the input. Now, I think that's probably enough for today's lesson. The thing I wanted to see was what? That in the real world, we need people on the frontiers of knowledge who find the relationships and verify them. That's a very important job, and it takes a mathematical and scientific and logical mind to do that. What's important to notice, however, is that once that relationship is there, and you have every reason to believe that it's correct, it does not take the same kind of initiative to apply the formula as it does to invent it. It's a different skill altogether. And what I want you to see is if you're afraid of formulas and you say things like, I could never have developed that formula, that in itself doesn't mean that much. The important thing is, given the formula, can you learn to play the game of algebra sufficiently well so that you can manipulate from the formula into finding the information that you want? And the rest of the course is going to be sort of based on this, but we'll talk about that more next time. But for now, just keep studying, right? Learn a lot and stay young. See you next time.